Okay, so good day, everyone. We are going to prove that this statement, the not of P or not Q, or not P and not Q is logically equivalent to not P. Okay, so we will first look at the first statement. We have the not of P or not Q. So what we can do is use De Morgan's for this. We will simplify the statement by distributing the negation operator to the factors. Okay, so this will result to not P, and this operator will be negate, will this or will become and the not of not Q. Okay, and let's just copy the second statement, not P and not Q. Okay, so let us simplify this further. So we have the not of not Q may be evaluated into Q. Okay, so we will have not P and Q. Okay, using the double negation, or simply copying the second statement, not P and not Q. And now, do we see a pattern? So we see that the not P and are present on both the sides. That means that we can use the distributive na operator. Okay, so we have the not P and Q, copying this, or not Q. Okay, now let's just write down first what we have used to review. So in here we used De Morgan's. And here we used double negation to simplify not of not Q. And for this, we use the distributive. And now let us evaluate Q or not Q. So taking the disjunction of a certain statement with its negation will give you a what? Will give you a true. Okay, so this will evaluate to true and not P. Okay, so this will be, we have used here the negation law. And not P and T will be equivalent to not P using the identity law. Okay, so now we have proven that it is, they are logically equivalent. Now moving on to the next example, we have the not of not P and not Q. Is it logically equivalent with P or Q? Okay, so let's solve it. So we can use again the De Morgan's. We will simplify this by distributing the negation operator to our factors. So we have the not of not P, and this operator or will become or in the not of not Q. Okay, now we will simplify. So the not of not P is equivalent to P, and or the not of not Q is equivalent to Q. Okay, so we basically used De Morgan's for this, and then for this simplifying, we use the double negation. Okay, so now we also have example 11. So we will try to simplify or prove that the not of P or of not P or Q and Q is logically equivalent with not P and not Q. Okay, so let us move on. So we can use again De Morgan's for that. So this negation operator can be distributed to the factors of the OR operator. So it will be distributed to this and to this whole factor. So this will have the not P, and this OR operator will become AND. And now we have the negation to this whole not P and Q. So we have the not of not P and Q. Okay, so now we have the not P, and then this negation operator can further be distributed to our individual factors. So we will have the not of the not P, and this operator will become OR and the not of Q. Okay, so we have this. So now let us further simplify. The not of P and the not of not P will be P or not Q. Okay, so now we can use the distributive laws for this. So we will basically distribute this not P with this factor to this, to both sides. So this will result to not P and P, then copying this, or, and then not P and not Q. Okay, so the not P and P will result to false. Okay, not P and P will result to false, or not P and not Q. So not P and P results to false using the negational law. Okay, now we have the false or this whole statement. So this will result to not P and not Q using the identity law, which proves that it is indeed logically equivalent, right? So we have the first statement, we used De Morgan's. And now the next statement, we used De Morgan's again to further simplify. And for this, we used the distributive. And then we used distributive law. Now for this, we use the negation muna. Negation. In this one, we use the distributive. And for this, we use the negation. And the last is we use the identity law. Okay, so that is the last example that I'm going to show to you in proving logical equivalence of statements using the laws that I have provided. Okay.